Welcome to Breadboarding. This is part 2 of the Fixing Video Snow video. That's video 22 of the Nanocomp 6809 breadboard computer series. So if you haven't seen part 1, I suggest you click the links above to go and watch that first, otherwise this isn't going to make too much sense. So in our overall plan, we're on step 22, fixing the video snow. So this is the interference that we get on the video output when the video RAM is being updated by the CPU. And this was a common problem that early PCs had, and in fact the IBM PC CGA adapter suffered from these issues and needed a number of workarounds to avoid it. So in the first part of the video, we've tested the various current video modes using the Tetris Lunar Lander and the Doom 256 colour title image screen, recorded all the traces, we've done some analysis and actually started to try and fix the snow. And in this video we're going to continue to fix the snow and then do some testing. So in the previous video I did some software checking for the vertical sync blanking period. So this is the most common way of addressing video snow, is only updating the video display at the period between the end of the screen and the start of the next screen. So that's sort of 50, 60, 70 times a second. And normally that's only probably about 1.6 milliseconds, about 10% of the overall screen refresh time. So we have to squeeze all the screen updates into about 10% of the time available. Now, when I showed this in the previous video, I did have some problem with the hardware handshaking that meant that I had to slow things down quite a bit. Now I've managed to resolve that. In fact, I'll show you in a minute, if you have a similar issues with any of your USB to serial converters, how you can address this. So I'll show you that in a sec. And then I was also looked at all the complicated timing around the CPU E signal, which is used to control when we read and write to the video RAM, and how that varied depending on where it was in the current video dot clock cycle. What I'm going to do in this video is program a couple of PLDs to try and address that. I was looking at the ATF 2500, which is a slightly larger chip, a more complicated chip, but I had a few problems with getting those programmed. So rather than spend any more time on it, I decided to go with 2 PLDs rather than the one larger one I showed last time. So let's have a look at where we've got the serial port. So this is the serial adapter I'm using. So this is a pretty standard FT232RL, I think it is, the chip on this. And if we just take this out, you can see that I've been using the 6 pins on the bottom there. Now the only issue is that although the clear to send signal comes out there, the only other control signal comes out on the bottom there is the DTR, data terminal ready. And unfortunately that's what I was trying to use and it wasn't working. Now it turns out this particular model here has blank holes along either side here. And what I've done is, you can see there's labels there that show that all of the other signals are actually made available on those pins. And it just so happens that the request to send RTS is made available there. So all I've done is I've unplugged the connection to the DTR pin and plug this yellow cable over from the request to send to the clear to send over here. So generally when you're wiring up 2 bits of equipment, unless you're dealing with a modem, generally you need to do a crossover connection or a null modem cable, and that basically means that the transmit goes to receive goes to transmit, clear to send needs to go to request to send, and request to send goes to clear to send. So you just have to cross them over when you're hooking up 2 bits of data terminal equipment. So I'm just going to plug this back in. So we've now got the hardware handshaking is in fact configured. I'm going to just plug in the the serial cable. Right, so what I'm going to do now is to rerun the test program that I was doing, only now what I've done is enabled the hardware flow control. Show the minor updates made to the code. So basically you've got a pause serial and continue serial, and all this does is the routines at the top here. So all they do is either make request to send high or make it low. So to pause we send request to send high, to continue we make request to send low. Generally RTS is always low unless we expressly do otherwise. The reset normally sets RTS low. So basically all we're doing is, once we've actually read a row in the S-record file, we pause the serial connection. We do then need to get the next 2 bytes because it takes a couple of bytes before it actually stops sending the data. And then once we've actually gone through and updated the screen data directly, we continue the serial, and that basically sets RTS low, so it allows the data to continue flowing. And if we didn't do this, so what was happening is we were missing a couple of bytes, and then what would happen, the S-record checksum would fail and it would abandon that particular row. So when data was coming out on the screen, you'd end up with chunks missing, so sort of gaps in the video display where it wasn't getting the data. So what we're going to do is to run this up on the Nanocomp, and we'll switch over to show the video capture. And when I did this last time, I think it took 2 minutes 15 seconds, so 135 seconds with the extra delay I needed to put in at the end of each line. So I had a few problems using the Realterm program I was using when it was doing large file transfers with the request to send, control to send, CTS, RTS handshaking. What seemed to happen, it was using some sort of large buffer and it would time out after a certain period of time. So I'm just trying out another terminal emulator here. So this is, it isn't quite as useful for the sort of things we're doing, but I just wanted to try out a different terminal emulator. So as you can see here, it's running on COM port 5. We just need to make sure it's running at 57.6K. We're going to be using output flow control, and RTS control is handshake, so that is what we want. So I'm just going to send down the program first, so we just need to send file and find where our file is. So sending it down, and that is in fact loaded. And if I just run up the program, we'll see on the screen it doesn't handle the line feeds quite as well as the other one, but what it should be able to do now is if we go to send the S-record file, so you can see this is now sending, and if I switch to the capture card, you can see that's now loading, and I'll time this from the video. It should be about 65 seconds from what I experienced previously. Okay, and that's completed, so I will confirm the timing. That seems to have updated the screen without any significant snow artifacts, and it's done it, I think, at least twice as fast as when we were using Realterm with the extra delay on each line. In fact, that actually completed about 62 seconds, I think. Now going to have a look at the programmable logic devices. So we fixed the request to send, clear to send serial handshake. There was an issue with the Realterm terminal emulator that it seems to have some sort of buffering issue, that although it is doing the CTS monitoring, it seems to send all the data down to a large buffer through the USB, and that appears to then time out after a period of time. So we'll look into that later. So the next step really was looking at adding the CPU MRDY memory ready feature to the in clock signals, and that was something that when we looked at speeding up the Nanocomp to 8 MHz, there was a clock circuit that we had to use to generate the E and the Q clock signals at 8 MHz, and one of the optional bits of that was to add the ability to extend the E signal so that if you were accessing slower memory or peripherals, then it could slow down the memory access to give those peripherals time to respond. But in fact, in this particular case, what we can do is to use this to delay the CPU from accessing the video RAM, so that we can let the video RAM finish doing what it's needing to do and then let the CPU have access to it after that. So that's what the diagrams and things we did in the previous video was all about. I'm just going to quickly show you what the changes we need to make to the in clock circuit, and then we'll have a look at programming the PLDs. So this is the part of the circuit that we did last time. So basically we're feeding in our 8 megahertz oscillator in this particular case into these two flip-flops, and we get an output here, which I think rather than using a transistor, we used an HC inverter, I think, which provides the higher voltage levels which is required for the E input signal into the CPU. But this circuit up here is what we're going to need to add, and that's basically another flip-flop with a NAND gate and an inverter, and the MRDY signal, when that comes in, when it's high, then everything operates as normal. When MRDY goes low, then it will extend the bus cycle for the E by a number of the clock cycles here. So depending on how long MRDY goes low for, it'll extend by 1, 2, 3 or 4 clock cycles. There is a limit. I think the maximum is about 16 clock cycles I think it's allowed to go, but hopefully from the analysis we've done, we only need 1 or 2 clock cycles to be added. And it basically allows the CPU access to slot in with the video CRTC access. If you remember last time, I did a rather scruffy diagram of the various timing signals, and what I have done now is tied that up a little bit. So this summarizes the signals that we need to do. So what we were looking at is the varying dot clock cycle through the CRTC depending on which clock cycle the E signal went high. So when the E CPU signal went high on the clock cycle 0, 1 to 7, then we're able to work out whether or not we needed any extra CPU clock cycles. So that's the 8 megahertz clock. So the first two we needed 1 clock cycle, the next 3 we didn't need any, then 5 and 6 we needed 2 clock cycles, and 7 we needed 1 clock cycle. And that's what all those charts and diagrams I did in the previous video were to work out. Now at the moment I'm planning to have the MRDY start on clock cycle 3 and end on clock cycle 4. Y0 will start on 6 and end on 9, and the video read-write signal will be kind of a 2 clock cycle within that Y0 period here. Now we could actually change these numbers if we find that the time is not quite right. We can change these numbers relatively easily and configure the PLD to adjust the timing. Basically we've got 3 groups of clock signals here. So the blue ones have the same MRDY cycles and the same configuration for the start and end for the MRDY, Y0 and VRW signals, and then we've got the 3 0 MRDY ones, and then there's the 2 here. So basically each MRDY CPU clock cycle is 125 nanoseconds, which is approximately 3 dot clock cycles. There is a 5 nanosecond difference, but in the grand scheme of things that shouldn't hopefully make too much difference. And basically what we're going to be doing is counting the dot clock cycles from when the E signal goes from low to high. So that's when we're really accessing the video memory. And if MRDY is enabled, the E high signal that is then extended by 3 or 6 dot clock cycles. We zero the dot clock cycle count when E goes back to 0. And then we're also then going to take the QA, QB, QC, CRTC clock signals. So that's the 25 megahertz dot clock divided by 2, 4 and 8. QC is also the character clock which is used for the CRTC. And we're going to be latching those when the E signal goes from low to high, and they're going to be known as EQA, EQB, EQC. So we're using the clock is the E signal, and then the PLD configuration is going to use the .D register, so the D type flip-flop for QA, QBC. And then we're also then going to need to maintain that at the start of every E cycle we zero a 4-bit counter, and we count the number of dot clock cycles from when E goes high, but we only count those dot clock cycles when E is high. So we need to combine the dot clock with the E signal, and we then use that to clock this particular latch. So what this basically means is what we need to understand is when E goes high, what was the cycle that the CRTC was in? Is it in one of these 0 to 7? And then dependent on that cycle, we're going to count the number of dot clock cycles from the start of that cycle, and depending on the number here, we'll choose at where these various signals are going to start and end. So it's quite tricky, but I think when you actually see the rules, you'll see that it's a bit simpler. Now I started to try and get the 40-pin ATF 2500 configured for this, but I had a few problems with it, and rather than spend another day or two, week or two trying to fix that, I thought, well, I know I can get this working on the older chips. The only downside of the older chips is that this chip is able to have multiple clock signals for the flip-flops, so we can actually have multiple clocks driving the various signals here, whereas for the older chips, then each chip can only have one clock. So the way how this has been split down, because we've got to have a clock based on the dot clock gated by E and another one with a clock based on just the E signal, what I've done is broken this down into two chips. So number 2 is actually a little bit simpler, so we'll cover that one first. So all this does is has the E signal coming on the input, then we have these QA, QB, QC, which are the divider outputs that are driving a lot of the CRTC circuits, and QC is in fact the character clock. We also need the dot clock as well, and I'll explain why we need that in a second. And we've also got one of the outputs from the other chip, because we ran out of outputs. Then the SNO Y0 value, we also need an inverted value of that, so we're using this as an inverter. And this dot clock signal, again, because these chips are a bit more limited, that in feeding the pin 1 here, we really want to make sure that the signal going in here is exactly what we want. Now the E signal is exactly what we want for this one, that when E rises, we will latch the QA QBC on the E QA QB QC. But this dot clock here, when we get to the other chip, we actually only want the dot clock to count the cycles when the E signal is high. When it's low, we don't want it to count. So that's the reason why we have to combine the dot clock and the E signal here, and we'll have a look at the rules down below. So basically it's fairly simple. The clock is E. We're taking the D flip-flop input for EQA from QA, QB, QC, and the E dot clock signal is just the dot clock ANDed with the E signal. So basically when E is low, then it will be no clock, and when E is high, then we will get a clock. And then finally, this is just the inverter. So this particular chip's quite simple. We've got quite a lot of unused pins here, but because of this clocking requirement, we can't actually combine the two. And then the other chip we've got, SNO 1, as I've called it, this actually takes the E dot clock that we created in the previous chip and feeds it in here. So although this is based on the dot clock, it will only be clocking when the E signal is high. Then we have the standard E signal, read write. We then have the latched QA QBC signals coming in from the other chip. We've got the Y0 signal coming in from the current address decoder, and the rest of these not connected. Then the main things we want out of this are we want the SNO Y0 signal, the VRW signal, and the MRDY signal. These are the main outputs that we're doing. So effectively what we're going to be doing is replacing the current VRW signal with this one. The Y0 signal comes in here and is going to come out as a SNO Y01, so it will be modified to fit in with everything. And we also know that as a result of the MRDY changes, then that will also alter the E signal coming in. So it's kind of quite a complicated feedback loop. Now, the other things we've got here, I'll explain the ones above here in a minute, but basically this is our dot clock Q0 to Q3. So this is just a counter going from 0 up to a maximum of 15 in this particular case. So it's just counting the number of dot clocks from when the E signal goes from low to high. And we'll see the rules for this down here. These intermediate terms here were necessary because some of the rules were so complicated. There were too many combinations, so I had to create these intermediate dot clock signals. And what these basically say are if we've got dot clock period 6 to 9, 3 to 6 or 9 to 12, then these signals will go high. And if we go back to our things here, we can see here that there are various combinations here. So the we've got the sort of combinations of things that we needed from here, and all I've done is simplified some of the rules so that we don't actually max out the number of connections. So you can see there's a 6 to 9, 9 to 12, 3 to 6 here. Some of the other ones were simple enough that they didn't need this aggregation, but this was necessary because we ended up with too many terms in the PLD configuration rules. So we've got definitions for the inputs and the outputs. So we've got these, the EQ cycle and the DC cycle. These are just decomposing the binary inputs into numeric inputs. So it just makes the configuration a little easier. This is the fairly standard sort of counter. So basically the counter values are based on the previous inputs. And there's also the clear. So what clear does is when clear is set high, then it will result in the counter being cleared. And in this particular case, we want clear when E is 0. So it's a two inverts here really, but this was the condition that I had previously. So it was easier to keep this logic. I guess I could probably just say clear is equal to E. So what this is doing is just counting the number of clock signals when E goes high, and it will zero out this when E goes low. Then we've got our intermediate terms. So these are the dot clock cycle 6 or 7 or 8 or 9, and 3, 4, 5 or 6, and 9 to 12. So with these extra OR terms here, they would explode the number of combinations, and the PLD wasn't capable of storing those combinations. MRDY had a slightly simpler one, so those can all be done within here. But the SNO Y0 signal, this is the one that needs these intermediate terms. So what this has done is reduced these by an order of 4. So it makes things a little bit simpler. And then the VRW has very similar. So basically the rules that we've got on the spreadsheet here are encoded into the PLD here. And what I'm going to do now is to plug these in, and we're going to test the second one first. So we want to make sure that our dot clock is gated by the E signal, and also that the value of the QA, QB, QC is latched at the rising period of the E signal as well. So I've taken out the disk controller board from the top of the board here, just so I've got a bit of space to put this in. Wired in a dedicated power connector with the Hack Modular breadboard buddy there. I've already wired in the ground for the logic analyzer. So this is chip 1, which has most of the stuff for the output there, which is what we're going to be feeding back into the video controller here. But this one here is the one we need to do first, because we have a clock signal coming out of here that needs to feed into this one. And there's some of these intermediate outputs here, the EQA, EQB and EQC, that also need to feed up here as well. So I'm just going to wire up this one first and then put the various connections from the motherboard in here, and then we'll have a look and see what the signals look like. Just going to do the power first. That's ground there. I won't wire the other chip up at the moment. Leave it disconnected. Okay. So we need to plug in the E signal. So I do already have a cable that's coming from E somewhere here. This is coming from E. So I'll plug that in quite close. Then we need QA, QB and QC. So I know that QC is the white one. QB, black one. And then QA is the grey one. Just plug this into. Okay, so we got E, QA, QB, QC. Now we need the dot clock. I have a lead here from the dot clock. Okay, so let's take a look at the logic analyzer and see what signals we're getting out of here. So if I just run this, so this is just taken a snapshot from the system running at the moment. So what we got up the top here is the E signal. So this is the CPU sort of signal, and the period when we're reading and writing to the video RAM is when this is high. We then have the dot clock. So this is the clock from that determines the pixels on the screen. So that's 25 megahertz. If you look at the top right up here, we can see that's 25 megahertz. Then we've got the QA, which is that divided by 2. So you can see there it's about 12.5 megahertz up on the top right there. Then we've got it divided by 4, so that's about 6.25 megahertz. And then QC, which is also the character clock, and that's about 3.1 megahertz. So these are the clock periods that we're getting from the CRTC controlling circuits. And the issue here is that the E signal and these signals go in and out of phase. And what we'll be able to see with that is the two sets of numbers. So if I just show over here, we've got two analyzers here, one showing QA to C, the other showing the EQA to C. So that's the QA to C signals latched by E. So you can see that when E goes from low to high, then these down here should be being latched. So if we add a timing marker at the beginning of these two periods here, just to have a look. So these are the rising parts of the E signal, and if we go in here and look at that point in time, the QABC signals are resulting in 606, and then if we look down the bottom here, what value is being latched here? Yep, we've got 6. And then if we go up here, this signal here is right on the boundary, in fact between 2 and 3, and generally I think when something's right on the boundary, it's probably going to take the value to the left of the boundary. So that's right on the transition. If we look down the bottom, we will see that the value down here is in fact 0.2. And if I change the decoded results here, so we only see the lower results here, we can see here that the sort of the starting E cycle is 4152730 So it's there may be a pattern to it, but it's not a particularly straightforward pattern. So this is the number effectively that's going to determine the set of conditions that we need to choose for our signals for the read-write, video read-write, and the Y0 signals. And so the output here of EQA, QB and QC is what's going to be fed into the other PLD device, and that's how it's going to know what was the starting dot clock cycle when the E signal went high. And if you remember the charts that we had previously, we'll just show one of those. If you remember from the previous video, we did this sort of graph for all the E0, 1, 2, 3, 4, 4, all the way up to 7, and we worked out where the memory ready Y0 start, Y0 end, and the video read write start and end signals were all going to be. So basically this number here is what we have on the screen here. So this number here is in fact that E0 to E7. So this part seems to be working okay, and then if we also look down the bottom here, we can also see that the E dot clock, and that's basically the dot clock ANDed with the E signal. We can see here that we've got a situation, I don't think the cables might need to be shortened and might need a bit of a boost because I'm taking some of these signals from quite a long way away from the actual source of the clock. But you can see here that in general, if we actually change this to glitch filter settings, we just take that glitch down. There we go. I think the glitch filter settings are probably been messing up. But what we can see here is that our dot clock signal that we've got there is being gated by the value up here. So if we were to add markers there and there, we can see down here that the clock signal is being controlled by that, and this clock signal is needed to feed into the other PLD because it's going to need to keep account of these dot clock cycles and wants to start counting from when the E signal goes from 0 to 1. So that's what we're going to look at in a minute. We're just going to wire that one up, and we're going to have to then wire some of the signals coming from the PLD who's just plugged into the top one. So what I'll just do is I'll probably just speed that up as I wire it in, and then I'll commentate over it. Okay, so just connect up the power and put some decoupling capacitors in on the ground lines. Now we're connecting the E signals together between the two chips, taking the latched QA, QB, QC output from one chip to the other, then the gated dot clock, then the feedback for the SNO Y0 to be inverted, plug in the E, read, write, and some of the logic analyzer signals. Okay, so I just tidied up one or two things here. One or two of the logic analyzer cables weren't quite in the right place, and I had to update the PLD configuration for the PLD number 1 because there were a few things I hadn't quite got right. But now hopefully what I'll show you is it up and running in its test mode. So at the moment the outputs from here are not feeding back into the video card at the moment, but it's allowing me to sort of make sure that the signals look sensible. And ultimately what we need to do next is to enable the MRDY logic on the main CPU clock, so that when we do try to extend the E signal, then it will actually take the MRDY signal out of this circuit. So I'm just going to do is to power on the NanoComp, and then we need to download the test program, because the issue here is that unless we're actually accessing the video RAM continuously, then we won't actually see any of the conditions that we're looking to do here. So I'm just going to load and sending the test program that we've got, and then what I'm going to do is to run that to the high-res graphics, so where we see the dashes running on the screen. So we'll just switch over to the capture card, VGA capture. So this is the screen we want. So that's basically just accessing the video RAM on a continuous basis, and we can obviously see the SNO there. Now obviously once we've enabled these changes, hopefully we would no longer see that flickering on the rest of the display here. It will just be the little line at the very top of the screen. So I'm just going to run the logic analyzer and capture the data. So we don't need very much. So if I just go through and explain what we've got here. So we've got let's just zoom in on one particular part of the signals here. So what we have here is a read followed by a write. And we can see here, because we've got the original Y0 signal, so the original Y0 signal is just coming from the address select for the video RAM combined with the E signal, and then it goes low. So effectively this is indicating that the CPU is trying to access the video RAM. And if you can see here, we've got the character latch clock, and when we were looking at the analysis here, we saw that we would get the SNO effect when accessing the video RAM, so Y0 and the video read write went low around the latch point here. So at the moment you can see that this would potentially have ended up with this particular scenario. And we can also see here that for the cycle that the CRTC was on when the E signal went high, so if we put in a few markers here, so when the E signal went high, then in fact it was on the 7th cycle, and so what that would indicate is we want one MRDY pause and the actual numbers that we've got for this, if we look back at our spreadsheet here, we'd want MRDY to start at 3 and end at 4, and these other ones to start at 7, end at 8, start at 6, end at 9. Now the only issue at the moment is because the clock is not being extended, because we haven't wired up the MRDY circuits yet. So at the moment there's no way to extend the E signal. So what would happen under the circumstance where MRDY was going low here, we would expect to see another 125 nanoseconds put onto the clock here. So if I draw another line here, so that would effectively come to, so that's 265. We'd expect that to be about 390, I think. So we'd expect that to extend out to there. And because that clock would extend out to there, it would hopefully mean then that our snow signal and if we were writing on the right signal, would actually be in this period here, which is between the character latch signals. So looks like that's actually working. We've also, so in addition to this is the effectively E0 to N here, and this will be 0 to 7. At the moment, up here we can see that the dot clock count from the start of E is starting at 0, 1, 2, 3, 4, 5, 6, 7, and then when E falls, then it clears to 0. Now at the moment, because we haven't got the E signal being stretched, then we'll never get to 8, 9, 10, 11, 12. So some of the signals we're not going to see fully here until we have actually got the memory ready signal. But what it does indicate is some of the key things we were looking for is that we get a memory ready pulse. And if we just go to some of the other signals, so if we go to, we need a memory access where we've got a different, there we go, let's go to one where we don't actually have memory ready. So for our E3 situation, that one was such that our timing and logic said we didn't actually need to include any memory wait states here, so MRDY values. So if we just put the markers here to the Y0, and we can see here that the snow Y0 is obviously quite a bit narrower than the original Y signal, and the video read write is obviously within the snow period, but also that within the bounds of the logic analyzer, that in fact this is actually going to be falling within the character latch value. So again, this looks like it should be doing what we want it to, but until we've got the MRDY signal being fed into the CPU clock, we're not going to fully see the whole situation. And then what we would expect to see is when we did have the MRDY going low here, we would expect to see this be extended by 1 or 2 CPU clock cycles, which is what 8 megahertz, 125 nanoseconds. So we might see it extend up to there, and under that circumstance then we would actually see some of these things moving around, and we'd also see here 7, 8, 9, 10, 11, 12, 13, 14, 15, potentially up to about 12 or 13 coming up here. So that's what we're going to do in a minute. So I'm just going to do now is to have a look at the circuit for the E clock signal MRDY. So this is a circuit, this is the one that we've already got, and at the moment these 2 pins here are tied to high. So if you see at the moment, the optional circuit is not included. Clear and pre-inputs of U2 and U3 must be tied high. So pin 3 and pin 7 here will currently be tied high, and they will need to be hooked into this little bit here. The MRDY at the moment, if we keep it as it is where it goes low, which I think is the convention on all 6809, designs, then we should actually have a situation where when this goes low, then we would get one or more of the oscillator cycles added onto the E signal, and what that should do is also extend the Q signal as well. So both the E and the Q should extend when the MRDY goes low, so where we get this stretch period effectively here. So that's what we're going to do onto the clock area of the board in a minute. Okay, so this is the diagram. Now the only thing we have to remember is that couldn't get any 74LS76s, they don't seem to be available anymore, so we're actually using a 109. Now the only thing about the 109 is the K input is actually inverted, so rather than working off this diagram where we may make some mistakes, what I've done is I've updated the KiCad diagram. So this is our original diagram, and all of the things are actually correct in here, and what we actually have to do here is connect the clear and pre-select lines for the two flip-flops. So number 1's on the left, number 2 is on the right, and those need to be fed to the output of the 74LS74 flip-flop. And then we've got the MRDY signal comes in here, so when it's low it's going to extend the cycles, and then we've got this three-way NAND gate coming in from the inverted Q signal from flip-flop 1 and going to the normal Q signal for flip-flop 2. And then we have a feed of the 8 MHz CPU clock going into the clock, and the output here goes into the D latch input, and then the set and preset are both set to 5 volts to high. So hopefully this should be relatively straightforward to hook up. And what I'm going to do to start with, I'm going to wire MRDY to 5 volts, so everything should carry on as if nothing else has happened. It should be unaffected by that situation. And then what we'll do is we'll wire on the MRDY signal from our SNO cancellation circuit and see whether or not that actually extends the E clock signal. Okay, so I'm going to put the NAND gate chip here. We're going to be using one of the inverter gates up here, so the input for MRDY is actually going to be coming into this gate here. So we just need to disconnect the tying that to 5 volts. Just make sure the other input is tied to 5 volts. Okay, this is our MRDY input that we're going to wire up in the future. And what we need to do is to wire this pin round to one of the things down the bottom here, and then the outputs of here is going to go into D. We're not using this side, the flip-flop on this side, so we'll be using these signals here, and we just need to make sure we wire them into the appropriate place. We also need to make sure that we get rid of the clear and the preset wires on here, so rather than wiring these to ground, they're going to be connected to the Q output over here. So I'm going to do is to wire that in, and then we'll come back and then fire up and see whether or not the clock signal is still working. Just plug the chips in, and we'll put in the power lines and the decoupling capacitors. Then we're going to take the 3 input signals down to the 3 input NAND gate at the top of the first chip there, and remove some of the pull-ups and put new pull-ups in. So that's the first of the leads into the 3 input NAND gate. Then we need to check those off. Then we've got the output going into the latch there. Then we need to check the clock signal, and so the other Q signals, and then the feedback. Okay, so I completed the changes. I'm just running the test program here, you can see there, and if we just have a look at the logic analyzer, you can see that our E signal looks to be behaving itself. We do have some MRDY signals down here, but there's nothing happening here, which is what we'd expect. So what I'm going to do now is to wire in the MRDY signal over to the output from our new snow circuit, and we'll see whether or not we get any change in behaviour. Okay, after wiring in the MRDY circuit, what I have done then is a round of fixes and things, which I'll summarise in a minute. But just to show you, this is a trace from the most recent run. You can see here the normal E clock signal is high. If you look on the right hand side over here, you should be able to see it's about 260 nanoseconds, and the full cycle is 500 nanoseconds, so that's about 2 megahertz, because we've got the system clock running at 8 megahertz and it divides it by 4 for the 6809. And we can then see that we've actually got the video Y0 memory select signal here, and we've got our snow Y signal here, and the video read-write signal as well, which is shorter than the normal read-write signal. And what we can tell here is that this E clock cycle has actually been stretched. So you can see normally it's 260 nanoseconds over on the right hand side here, and now it's 510 nanoseconds. Now when I was playing around with this, the cycle stretching circuit, I wasn't able to get it to extend just by one 8 megahertz clock cycle. It seems to be going 2 clock cycles, 250 nanoseconds. I haven't spent too much time trying to get to the bottom of that. So where we have the MRDY signals, it doesn't really seem to matter too much whether or not it's the narrow one or the wider one. We still get the 250 nanoseconds extra clock. So it's sufficient for what we need. The number of times that we end up with this stretching circuit working is not that often, so it's not going to have a dramatic influence on the performance of the system. And so you can see here where I've drawn the timing markers on either side of our snow Y0. You can see below, this is what the Y0 signal would be. However, the normal Y0 signal would stop actually at that point there, because it would only be as wide as the E signal normally. And you can see now that the boundaries of where the character latch is here, that the Y0 signal fits comfortably inside there, and then the write signal in there as well. And what I have done is for each of the clock cycles, so you can see here, because I'm combining the Y0 signal, so if we look at the decoding of the clock cycle of the CRTC, so that's the latched QA, QB, QC from the E signal, I've combined that with the Y0 signal there, and what that means is we're only interested in when that value is 0, and so anything which is actually with a leading 1 we can ignore. So you can see here that all these ones with a leading 1, that's when the video RAM is not being accessed by the CPU. So just by looking at all the 0x zeros, we can actually look at only those memory cycles where the video RAM's being accessed. And in fact, if we look at 0, then we can just look at all the 0 ones. So I've gone through and put marker pins on all of the different values here. So we've got the zeros here, and we can see here that the bounds here are comfortably within the markers. It's quite interesting if you want to you can click down through all these very quickly, and you can see that the yellow Y0 thing is comfortably within the 2CH latch values down the bottom. So that's for a large number of values as we're flicking through there. So now if I go to the number 1, so you can see for number 1 we've still got the stretching of the E clock signal. You can see below it that the Q signal I've added here also stretches by a similar amount of time. Then we have the dot clock combined with the E signal here, which is what's used to count the number of dot clock cycles we have from the rising E edge. So you can see here that this starts with 0, 1, 2, 3, 4, 5, 6, all the way up to 0C and 0D. And we've got the memory ready signal here, which actually causes our clock circuit to extend by another 250 nanoseconds. And you can see here again it's comfortably inside. I had to do quite a lot of changing around with some of the parameters for the PLD configuration to get each of the values here to fit nicely under all circumstances. Quite often it would fit for probably 80 or 90% of the signals, but occasionally you get the one outlier that would actually stray to overlap one of the character latch trigger points here. So that's the B. If we look at C, again similarly, this C1 is for 02, so this doesn't have a memory ready signal here. So this one is just unaltered, so you can see here the E signal there is 260 nanoseconds, but again it fits neatly between these two here. If we look at D, so this should be 3. Again, 3 doesn't require any change to the clock timing, so again this fits in neatly as well. And if we were to look at all of these values, I've gone through all the values for each of these values and cycled through them all and checked to see that they're all within the bounds. So hopefully we shouldn't have any issues where the video access is interfering with the latching of data to go into the video display output. So then have a look at E. So this should be 4, and this required a little bit more messing around, but again this is slightly different from the other previous two, and I'll explain that in a minute. So we look at F. It's again 05 here, and this does have a memory ready signal here, and we can see that it's extended, and that in fact that our clock cycles here is between about 7, 8 and 11, 12. Some of these things are slightly delayed, so although the clock cycle might get triggered earlier, then by the time all the rest of the logic has sort of triggered, then it can be 20 nanoseconds, 30 nanoseconds afterwards. Remember, one of these clock cycles here is about 40 nanoseconds, and some of these gates have got delays of 10, 15, 20 nanoseconds, so there is sometimes a little bit of a delay from when something's triggered. Look at G. So this will be 6 down here, you can see, and again this is comfortably within everything. This one is also extended, and then finally we'll look at 7, and again 7 has got the MRDY and is between about clock cycles 7 and 0B. I've put 0A, 0B here. There was a problem I had, and it was because the configuration of the PLD takes hexadecimal values, and I was putting 101112, and obviously that was counting it as hexadecimal, and so it was resulting in slightly weird results. So the clock circuit now seems to be configured properly. I'll just show you a few of the issues I had to solve. So one issue I had, that I was having strange occurrences occasionally where the read-write signal here would change actually halfway through the E signal at the top here. Now generally the read-write signal should only really change sort of sometime in this phase where it's putting a new address on the address bus. The fact that it was changing in the middle of the E clock cycle here was strange. Then I had a look at the signals. There's actually a separate signal for the E feeding into the CPU because it has a slightly different voltage requirement, and what I found is that there was a slight glitch there, and when that glitch occurred it actually caused this read-write signal to finish early, and it was also messing up some of the other timings. What I also noticed is this original decoder Y0 here, this should be the address line combined with the E signal and then inverted, and so we'd expect this to end at the end of the E signal as well. So the fact that both this and this were not working indicated there might have been an issue with the timing signal here. So I rewired it slightly to make sure that both the CPU E signal and the main bus E signal were derived in the same way and went through the same buffer chips, and that seems to have resolved that particular issue. So it just goes to show, I mean, this gap here probably is about 10 nanoseconds, something like that, and 10-20 nanoseconds can cause problems like this, which wasn't particularly straightforward to get to the bottom of. Then there was another issue where I've already said that I was including in some of the conditions in the program or logic device configuration as 10, i.e. 10 rather than A, and in fact that 10 has been interpreted as 16, and so that was messing up some of the configuration. And in fact what I was expecting is that I should have had something starting around clock 9 going up to clock 12, which is C here, and in fact the bits that I would expect at the end here were in fact appearing here, and that was caused by the fact that obviously a 1 in front of it effectively was yeah, going back to 0 and counting again. So that was the reason why these 3 cycles here that would normally be expected to be 10, 11 and 12 were actually appearing in the wrong place. So by switching the configuration to use hexadecimal, then that fixed that issue. Then finally, with some of the combinations, as I was having to separate out some of the conditions and rules for the various E0 to E7 signals, so whenever the CRTC clock cycle was starting on the E cycle was starting on the different CRTC clock cycle. So this is our CRTC clock cycle here, and depending on whether or not the E signal was triggering at the start or end of that clock cycle, when I was changing the terms here, I found that I need to split out some of these a little bit differently, and because of the way how I was combining the various conditions, it got a situation where again we got this sort of 10 nanosecond spike here that was again going to cause problems. So what I ended up doing is just rearrange the way how the conditions were organized, and that has got rid of that particular issue. So it just goes to show, even when using these programmable logic devices, you do have to be mindful of some of these sort of issues with timing, and taking signals from different paths and things can sometimes have slightly different timings which cause this type of issue. But all these sorts of things now have been resolved. I'll just show you the changes to the configuration. You'll notice here on the pin definitions here that these are the dot clock sort of intermediate signals that I had to create because we ran out of terms in the PLD. So now this is dot clock cycle 5 to 8, dot clock cycle 3 to 6, and now dot clock cycle 7 to A. And that previously I think was something like 9 to 12 I think I had there. So I've made those consistent now. And some of the timings, so some of these are where these sort of timings had to be changed. Obviously I've now, rather than got 1 0 in there, I've now got A, and so that was one of the problems we've just been talking about. I had to tweak the MRDY signals slightly, so from where I showed you the data in the charts and the graph paper, then they have changed slightly. These YC0 signals have changed a bit. I've had to break out cycle 0 and 1 from cycle 7, and cycle 4 is on its own, and in some cases I've actually broken out individual terms here, but all of this is still within the number of terms that the PLD supports. The reason why I had to introduce these things here is that with these broken out into the DC cycle or conditions, then it ran out of the number of terms that it could combine into one. And then the VRW one was trimmed slightly. And I have now updated the configuration that I showed you previously. There's a version 2 of this. And basically, so the MRDY cycles, doesn't make any difference whether we have 1 or 2. It seems to end up with 2, whatever I do here. So I've discussed that already. So the start of the MRDY and end of the MRDY signals, it's changed a little bit for some of these. The start and end for these has also been tweaked a little, as has where the video read-write signal has been changed. So compared to version 1 of this, these have been tweaked quite a bit. I will share at the end of this, there's an updated diagram that I've done, so it was getting a bit messy, just to make sure all this sort of stuff is nice and neat. So what that means is, with the timing signals that we've got coming through here, we now should be in a situation that when the CPU tries to access the video RAM, so when the CPU accesses a video RAM, then the Y0 signal goes low on the main address decoder, and then we further then process that so that this Y0 signal fits within the character latching points here, and then it also creates the video read-write signal to also fit within here. So what we should be able to do is to replace the current feeds of the Y0 signal and the video read-write signal from the current address decoder, and we should just be able to replace them with these signals generated by this circuit, and it should just allow the updates to the video RAM not to generate the snow that we've been seeing previously. What I'm going to do now is just to wire in the outputs that we've got here for the Snow Y0 and the Snow VRW, wire those into the rest of the CRTC circuit, and then we'll have a look and see whether or not this has actually fixed our snow. So I installed the updated circuit and replaced the Y0 VRW signals and the not Y0 signals that were originally being fed directly out of the address decoder, and now swapped them over to the ones for our video snow circuit. I had to do a bit of tuning of the configurations once it's all wired in. There's a few extra delays and things through the various latches and things that meant that some of the timing that I'd done standalone I showed you earlier need to be tweaked slightly. So those values have now changed. In particular, the main things, I was able to make the video read-write signal to be 1 dot clock wide. When I looked at the data sheet, you only need about 10 to 15 nanoseconds for the data to be written to the video RAM. So I shortened that, avoided some of the issues I had. And then I've also changed some of these timings again to better suit the way how the signals were working within the video card. So what I'm going to do now is to show you the Nanocomp, and we'll just go through and run the test program, and then they'll go through and run the other programs that we're using at the beginning, just to see whether or not we've managed to make any difference to the video snow. So this is the test program. You can see it only does the X and the red there. The rest of the interference, the rest of it is not there. There's a slight little bit of flicker, but this is actually stopped updating the screen now. You can still see the minor little bit of flicker from time to time, but I think that might be caused by some of the clock signals. Probably need a bit more buffering because they seem to be getting a little weak, and that seems to cause some interference sometimes. So that was the character mode, so there wasn't any of the red update that we saw previously. This is the black and white high-res 2-color mode, and you can see here that we've just got the 8-pixel line at the top, and we're not seeing the lines flash across the rest of the screen. Now when we go to the high color graphics, then we still expect to see the interference there because we weren't able to do anything with the video timing for this. So you can still see that we've got the interference there when it's updating the video RAM, and when we stop then it sort of goes. But we'll show with the Doom image that with the better handling of the serial handshaking and the modified program there, that we can actually load the Doom image over the serial port during the video blanking period, and that will actually result in elimination of the snow. So I'm just now going to go in and show the other programs, the Tetris game and the Lunar Lander game. So this is the unoptimized Tetris game, and you can see that still occasionally a little bit of flicker, but it's very much better than it used to be. So that's the basic sort of initial version. Now you can see that there's very minimal flicker there now. Now this is the optimized version, so we just need to press S for start. You can see now that the flicker has pretty much been eliminated now, so that's good. And then we'll just do the fast version. So this is now the version which has got the highest rate. You can see at the speed that it comes down now, and there's virtually no interference there at all. That looks like that's good. So this is now the Doom high-res color, and I'm just going to download the file here. So this is now using the hardware handshaking on the serial port, and you can see now that it is downloading without any interference to the screen because it's doing it in a video blanking period. Just speed up the rest of the loading of the image here. So that's now loaded and set the color palette, so that has now done a lot better than it was previously. So now I'm just going to run up the Lander game, and this is much better. There is still the occasional minor little bit of flicker. It's not 100% perfect, but it's probably 90% better than it was before previously. And what I have sort of realised is probably it's got to the stage now where some of the more recent wiring is a little bit long and messy, and really it needs to be tidied up a little. The board needs to be tidied up a bit, and probably really lay out the whole board from scratch and actually try and eliminate some of the signal paths. I did have to modify the 25 megahertz dot clock and put some buffers on it to stop some of the interference that I was seeing. So what I'm going to do is to update the schematic diagram before I post it onto GitHub, and it will have some of the modifications I did for the circuit to get it working. But wanted to show you that I've managed to eliminate the majority of the snow, and this is the same sort of interference that the IBM CGA color graphics array card would experience. So it's possible to certainly eliminate the snow for two of the main graphics modes. Just the high color mode in this particular case I wasn't able to do. That in fact wasn't one of the original CGA color modes, it was actually an extended mode in the MCGA card, which came out I think with the IBM PS2 Model 30. So thanks for watching. If you found it interesting and you don't want to miss any future videos, please hit subscribe, and if you can hit like, I appreciate it. Just helps to make the videos available to a wider number of people.